Uh, Hello, my name is Bingqing Guo from MMV Group of Cornell University of London, and it's my honor to attend CIS Winter School. So, uh, here my topic is 3S-Net arbitrary semantic-aware style transfer with controllable ROI choice. And here I want to firstly introduce the style transfer. So style transfer means that we're rendering a natural image by a selected artistic style. And here is two kind of style transfer methods. The two objections. So the first one is single style transfer. So you can see here, we just use one style image and we have one content image, and here is the result. And we also have the multi-style transfer, so which means that we can use multiple style images. So here is a full style images and still one content image, and we can have multiple results because they have different weight of each style image. And the next is the neural style transfer, which means that we use neural networks to achieve style transfer. So they usually have three classes. The first one is optimization-based neural style transfer. So this kind of method usually generalize the transfer problem as a set of optimization problem, and they usually minimize the statistics between content image and style image, and for example, the content loss and style loss. So, but however, this kind of architectures require an optimization process when the content image or style image changes. So they usually are very low efficient. And the second method is to train a feed-forward network. So this kind of architectures usually are designed to capture the diversified style patterns, and in the meantime, they can preserve the coherent content structures. But many and also many feed-forward architectures can transfer arbitrary styles to the content image, but they still require training before application, so which is also time-consuming during their training process. And the third method is feature transformation based methods. So this one actually means that they just use feature transformations in the feature space, and they are true real-time and highly efficient, and they always balance the efficiency of the visual quality of results. So our work is the motivation of our work is to solve the problem of the multi-style transfer techniques. So usually the most multi-style transfer techniques just linearly combine the style features with weights, but they overlook the semantic relations between the objects. And our task is to develop an adaptive and flexible semantic-aware style transfer method. And we only need transformation in the feature space. And the key idea is we utilize different information encoded in each channel of features to perform effective semantic-aware style transfer. And also our model is capable of single style transfer and multi-style transfer, and also ROI style transfer, which means region of interest. So firstly, we design a framework called 3S-Net, and it includes it includes the style transfer module about two-step semantic instance normalization and the semantic style swap. And here, to our best knowledge, our method is the first to achieve semantic-aware style transfer without training a model. So this one is our framework. So our framework is based on here is a pre-trained VGG19 encoder decoder and a pre-trained DeepLab Pre3 segmentation network. And in the semantic objects matching module is here. So we generate correlation maps between different objects. So for each object, in the content image, we can find the corresponding object in style image with the highest correlation. So for this example, this one is a person and this one is a person, so they can match with the person and this person, the two people in the content image and the style image. So our style transfer module is here, and it is inspired by classic adaptive instance normalization, and this module includes two blocks of two-step semantic instance normalization and one block of semantic style swap. And then after 5 iterations, the final synthesized feature is decoded into a stylized image. So about the 5 iterations, because BGG19 has 5 convolutional layers. So here we generate semantic-driven channel descriptors first. So in here, UK is a one-hot mask generated by the segmentation network towards the object K. So here is, we call it a group. And the concept of these channel descriptors is usually introduced in image editing and image generation fields. So the channels in one feature encode different information. So in convolutional networks, different kernels react differently to the objects in the image. So we can have this weighted descriptors queue, and for each channel of the K group. So about this two-step semantic instance normalization module, so it includes 2 steps. So the step 1 is channel-wise. So here is we actually we coherent the statistics between the content and image from the channel-wise. So this one is pretty like the normal adaptive instance normalization. And the channels with higher weights contribute more to the representation of semantic objects. And the second step is group-wise adaptive instance normalization. And this one also considers the contribution weights of each channel, but it is group-wise. It see the object as a whole. So they calculate the statistics from the group-wise perspective. So this semantic style swap actually they transfer the patches from the style image to content image, and here we also just consider the group, the specific group K and the corresponding group K, KS in the style image, which is the corresponding object in the style images we found in the semantic, the matching module before. So here the qualitative evaluation. So this one is the single style transfer, some results of it, and we choose 3 representative methods, the style transfer methods, WCT, and the adaptive instance normalization, and style mixer. And here are 2 examples of we choose the region of interest. So here is we choose the background, and here we choose the train as the region of interest. And next is the multi-style transfer results. So here we use 2 or 3 multiple style images, and actually this one we choose different presentation, different comparisons of the methods, because like I said before, some modules are restricted by their module, so some methods are not cannot achieve multi-style transfer when they just designed to achieve single style transfer. And here we show examples of each block, the influence of each block to the style transfer results. And here we only achieve two-step semantic instance normalization. And here we add the semantic style swap. And actually, this semantic style swap, they because they transfer the texture of the styles, so they usually add more details of the style. And here there's the final result of this batch. And here we have more examples of this A and B are region of interest style transfer, and this one is single style transfer, and this is multiple style transfer. Yeah, that's all. Thank you, and thank you all for you
to
listen.
Yeah, thank you very much, Bingqing. Okay.